An hour's drive out of Bude, along the coast to the north. You get to Hartland Quay. Pretty dramatic. Reminds me of Southwest Ireland. You see some severe structural events here. So the Hartland Quay information board. On. There's Jonathan striding ahead towards those spectacular folded rocks in the cliff. It's a bit American. Strictly no dogs beyond this point. Interesting. Oh wow. You can see why it's a structural geology course.
Okay, that's a very basic cross-section through a generic mountain belt with a four-deep or four-land basin, however you like to call them. Okay, there's nothing specific to the Beriscan about that, but this just puts where we are in context. Thrust belt migrating from south to north. We're in the deeper, i.e. marine part of the 4D, where the flexural subsidence is greatest. But the fact that you're finding plant debris, and remember to the north of us is the South Wales coalfield, really exemplifies the geometry I've drawn here. So 4D deposits on lap onto the plutonic basement, as I've tried to show here. And it's in this area here where you'd have shallow water and swampy facies, deltas, coals, etc. So presumably that plant debris has been washed in from the north here. Okay, and obviously a very dynamic story because these thrusts with time these thrusts are propagating. I'll draw it slightly more exaggerated than I mean to. Propagating into the 4D. So partly the most proximal parts of the 4D basin become incorporated on subsequent thrust sheets and become piggyback basins. All that sort of stuff you might have seen in the South Pyrenees, for example.
Okay, a quick geological summary of Hartland Quay. These are Carboniferous turbidites, and we are on the northern edge of a large syncline. Carboniferous in age. These are called Chevron folds. You can see they're quite tight and fractured. And the degree of chevron folding is a function of the percentage and thickness of the sandstones. Apparently, this interval here, you can see a little bit of curvature on the top of these dipping beds. Is not to do with Carboniferous structural events, it's because of the soil above that pushing the top of the rocks down. And we're just going to go and have a look in this cave where we're going to see some turbidite structures, and also there's some terrestrial material apparently. So, on. Quite spectacular. Ongoing discussion about this inclined bedded unit and that supposed recent curvature at the top there, which I'm still challenging. This is the underside of one of the massive sandstone beds. You can see the scour structures. Well, talking with Jonathan Turner, he suggests that these rocks and the deformation were between 5 and 8 kilometres depth back in the Carboniferous. Okay, we've got to have a bit of geological orgasmatron. You see a chevron fold at the top and the axis, and then, oh dear, what's going on here? Quite spectacular. And there's some people for scale. So you've got another of the Chevron folds here, coming down into the axis. Here's the other limb. And what happens is that the sandstone, the reddish beds, slide over the thin shales. So if you try to fold a telephone book, where each page is a sandstone and the air is the shale, that's what's happened with these beds. So they've all slid a little bit over each other to be able to be squished up into these series of Chevron folds. And Jonathan was saying that these turbidites, 280 million years old when they were deposited, were started to be deformed when they were still fairly shallow, maybe 100 metres. So the deformation, the Variscan orogeny deformation, was ongoing. And clearly the sands and the shales had to be compacted to be hard enough to be compressed into the Chevron folds and fractures. So it is now, what is it, 1:30, and the sun's come round and it's showing the structures much better than when we first arrived. Okay, we're going to play a little game here. You've got to spot the geological feature. Then you have to name it. Well, it's 3:15, and having driven around the north coast a little bit trying to find this place, we're now taking the coastal path down to Milook. Change of plan. Milook is not affected by the rising tide. So I guess we're heading down there somewhere. So about a 5-minute scramble down. And Jonathan was saying the plan is to scramble back up, or you can bring the van down the single lane track. I wonder how the vote will go on the return journey. Not too far to go. So it's about 4:30, the sun has burnt off the clouds at Millook Haven. It's turning out to be a very nice afternoon.
Same formation as Crackington Formation. It's relatively, and you'll see what I mean by relatively tomorrow, relatively low net to gross, if you like, relatively thin sands. Remember, it's the sands that are controlling the fold geometry to a large extent. And flexural slip dominates, the proverbial telephone directory process. The obvious contrast with where we were this morning is that the axial planes here are horizontal. Therefore, by definition, one of those two fold limbs is upside down, So this would be a case where you need to use whatever sedimentary structures you might find to determine way up. Okay, someone was talking to me this morning about using cleavage bedding angles to determine way up. You can only use those if you know grossly the way up of the section independently from sedimentary structures. Cleavage is a deformational structure. Folding is a deformational structure, so you can't use anything to do with deformation to tell you way up. So horizontal axial planes, as is clear. So these are termed recumbent folds, as opposed to this morning's folds, which are upright. Sort of similar tightness. We'll see tighter folds in thinner bedded, shalier Crackington Formation, a little bit south tomorrow. Okay. Someone spoke about divergence and asymmetry here, and you remember I drew the diagram of if the thrust transport direction is that away, the folds are long limb, short limb, long limb, short limb. There's clearly a long limb and a short limb, a long limb and a short limb here. So have a think about, I don't want to sort of tell you everything now, because I'm sure people will see at least as much as I see, but just have a think about what the fold asymmetry tells you. You'll also notice on one of those two sets of limbs, there's lots of veining, i.e. layer parallel stretching. On the other, there's no veining. And actually, if you look carefully at some of the sands, and I think you can see it from here, as you go from one limb to the other, the sand's thin. In other words, they've been stretched and thinned on one limb, and shortened and thickened on the other. So there's a clear shear sense here, and it'll be interesting to see what you get. It's quite a surprise in store when I reveal the answer at the end in a grand climax to the day. I will at some stage grab everyone.
So a little bit closer up, come down the sequence. So the axial planes of these chevron folds, no, they're not actually chevron, there's a long limb and a short limb. The axial planes are actually parallel to the ground, horizontal. Okay, the sun's come out and you'll have a geological narration. That folded sandstone there shows that the sandstone itself has deformed without fracturing. We didn't see that at Hartland. The sandstones were fractured there. So something has allowed these sandstones to bend in this location as opposed to fracturing at Hartland. And you can see there the thinner sands are also not fracturing, not fracturing to destruction, at least up there. They've got fractures infilled with quartz where they've stretched, but they haven't actually broken completely. So we don't really know which way up this massive sandstone is. This might be, we're looking at what appears to be a top, but it could be an overturned limb. And you've got shale fill into the fractures, and it's coming down to about there. That's about 2 inches. It hasn't been able to get into that, or that carried on fracturing. And the whole bedding plane has got this. Probably the shale that's been squeezed into those fractures is this shale here. Now here we have an absolute hero, cleaning up all the junk and crap off the beach, and that's where he's been. You see why it's called the whaleback. It was Alistair trying to kill a seagull successfully. Sunday 19th of June, yes, you can see what the weather's like. We are at the Bude whaleback. Beautiful anticlinorium, which means that it plunges to the right and plunges to the left. And you can see these bits also on the limbs of the anticlinorium. I'll keep saying it. And then you come over here and they're now dipping in the opposite direction. So there's probably a tight syncline down the centre of the view where I am now. Because here, these beds are now dipping to the left. So to set the scene, you come across Bude Harbour from our hotel, so we're going to the south of the Bude River and the harbour. So this headland here with the flagpole is on the southern flank of the river. Of Helena demonstrating the current friction coefficient and confining pressure on some fantastic joints. There we go. Brilliantly done. So on this south-facing limb of the anticline, a large amount of discordant fracturing. Jonathan's suggestion for that is that the effective stresses are all fairly equal, nearly hydrostatic, so that the fractures would go in the direction of the the least stress at the time, but there wasn't a consistent stress system. A dot instead of a circle in the Moore diagram. So this limb, or this massive sandstone south-facing limb, has disappeared. You see the expression of the axis of the anticline further down there past Dale. Yeah, we've got some absolutely beautiful structures in this thinly bedded silts and shales at the centimetre scale. Yeah, you can see a beautiful mini graben. Yeah.